Hello and welcome to another video lesson with Lawson. Today we're going to be looking at the vector a little bit closer, more specifically at the unit vector with a little bit of vector review. The first thing to remember is to be able to tell the difference between a vector property and a scalar property, or something in the universe that we would describe as a vector, or something in the universe that we would describe as scalar. A scalar description has magnitude only. It means that it's described by a number with a related unit. As you can see, there are several examples there. Early on in the course, you might just be memorizing the things that are scalar versus the descriptions that are vectors. As you get more experience going through the curriculum, you'll start to recognize the things that we represent using vectors and what are vector descriptions. Unlike a scalar quantity, a vector quantity has magnitude and a related unit. It also has some kind of directional description related to what it's describing. Again, you can see several examples of vectors listed below. The vectors we've already described are things like displacement, velocity, and acceleration, but we're going to get into several more as we go through the curriculum, looking at things like forces and momentum and field strength. Each time we introduce a new vector, we're going to use the same idea of how to represent vectors. It just simply will be a new part of the universe we'll be describing that's a vector description. When we're identifying a scalar quantity, we'll often just use the variable that represents it. Vectors are also represented as variables. However, to discriminate between a scalar variable and a vector variable, you'll often see that little arrow above it signifying that it's a vector. What looks like the absolute value of the vector is actually a way of just identifying the magnitude only, the value or number that would be associated with it and its unit, and not its directional detail. Sometimes we'll have a vector described but not actually have it drawn for us, and since the direction is important, we'll describe that direction in terms of a theta or a phi or some other variable that represents the angle either between a known horizontal or vertical axis. Three spatial dimensions. We have to deal with a horizontal and a vertical, but also one that's perpendicular to both of those, or one that would go into or out of the page if you already have one that goes across and then from top to the bottom. One of the things to think about when you're representing a vector that you've already seen in one-dimensional motion is it's simply an arrow. The arrow describes the two important properties, which are magnitude and direction. The length of the arrow indicates the magnitude. The longer the arrow, the greater the magnitude or greater the value associated with that vector. And the arrow points in the direction. So if we have an angle, like we see here, where it's somewhere above the horizontal, that would be either in quadrant 1, or somewhere north of east, or some polar coordinate between 0 and 90. The magnitude of a vector can never be negative. We can describe the negative of a vector, but the magnitude's never negative. The negative of the vector, as you'll see soon, is simply the vector that points in the opposite direction. Again, as a brief reminder, we're used to our Cartesian coordinate system, where we have a horizontal axis signified as an x-axis, a vertical axis signified as a y-axis, and a z-axis that's perpendicular to both of those axes and goes into or out of the page. In this case, we see that the x goes to the right in the positive direction, the y goes towards the top of the page, which would be the positive direction for the y, and that means the z comes out of the page or is a positive direction for the z. We'll go over how we can use the right-hand rule to identify the direction of the z-axis. The positive x is arbitrarily determined, and the positive y can also arbitrarily be determined. But once we've determined the direction of the positive x and the positive y, that predetermines what our positive z-axis is. Or if we know our x and our z, then we know the y that was required. Or if we know the z and we know the y, then we know the x that was required. One little note is that these vectors are drawn at a starting point. And as we can see here, this vector represents a velocity of 5 meters per second going in that specific direction. It actually means that at that dot, at that instant, the initial point or the tail of that vector is when the velocity is 5 meters per second. If it's accelerating, at any instant after that point, the velocity will no longer be 5 meters per second. So that vector doesn't show the velocity being smeared across the page. It's showing the velocity at that one instant in time, signified by where the tail of the vector is. When we have two vectors that have equal magnitudes and point in the same direction, they are equal vectors. Here we see two different representations of displacements. We refer to one as Bill and one as Sam. Bill and Sam both leave their home and walk in the northeast direction the same exact distance. Since they're traveling in a straight line, their distance is equal to their displacement, and since they've traveled in the same direction, the length and direction of each of their displacement vectors are equal. Therefore, the vector represented by B is equal to the vector represented by S, or those are indeed the same vector. Anytime two vectors have the same magnitude and the same direction, they are equivalent or equal vectors. As soon as the direction is changed, even if the magnitude is the same, or if it's in the same direction but has a different magnitude, it would be a similar vector but not an identical or equal vector. As was mentioned previously, we can talk about the negative of a vector. The vector itself is not negative. The vector has a positive magnitude. However, it can point in the opposite direction. So in this case, when we're assigning a direction as a positive direction, automatically going the opposite direction would be the negative direction. Here we see vector A that is also going northeast, similar to vector B and vector S. However, the negative of vector A would point in the southwest. So it points in the opposite direction, but it has an equal magnitude. So it's exactly the same length, simply points in the opposite direction. Another way of saying that is that we take the arrow and we put it on the opposite side or pointing in the opposite direction. We now have the negative of that vector. Notice, that's the negative of A. It still has the same magnitude as A, it just points in the opposite direction. That's the only reason we have the negative associated with it. The negative of a vector in the negative direction would be a vector in the positive direction. When we're describing vectors, one of the common strategies that we'll use is the unit vector. The unit vector has some interesting definitions. While it points along those x, y, z axes, or it exists in that three-dimensional spatial orientation, we don't want to describe it simply as being along the x, y, z direction. We're going to actually refer to them based on the unit vector. The unit vector points in the positive x, positive y, and positive z direction. And instead of referring to it, so we don't have an x of an x, we refer to the positive x as I hat, the positive y as j hat, and the positive z as k hat. One of the things that we're doing with the unit vector is really we're just looking at another way of being able to describe a vector in terms of its components. Here is our component form for vector r. R is shown as the component rx in the I direction, the component ry in the j direction, and the component rz in the k direction. The definition of the unit vector is that it has a magnitude of exactly 1. So if it's pointing only along one of those axes, then the two other components are 0. And in fact, any vector can be broken down into 3 components. It's just possible to look like 1 because the other 2 are 0. We don't generally include the zeros unless we're trying to make the point. However, we could have a vector that's at an angle relative to the x, y, and z axis. It doesn't point along any one of those axes or even along a plane between 2 of those axes. And if that's the case, then we're going to have both an x, y, and z component. The unit vector would point exactly along the direction of that vector, but have a magnitude of 1. All that simply means is that if we were to multiply that unit vector by the appropriate value or the appropriate quantity, we would get the vector that we're describing. And we can do that by simply taking the unit vector's components and multiplying it by the value needed to get the components of the vector being described. When we're describing it, again, we use the I hat for the x-axis, the j hat for the y-axis, and the k hat for the z-axis. More specifically, I hat points in the positive x, j hat points in the positive y, and k hat points in the positive z, which means the negative of I hat points in the negative x, and so on. This is a right-handed geometry. We can identify the relationships between the positive x, y, and z using our right hand, or the relationship between I, j, and k. What you want to do is take your thumb and point in the direction of the x-axis. Now again, we can direct that anywhere we want to. If we're trying to match the orientation on this screen, I've got to have the thumb pointing this way, coming out at a bit of an angle. Now I can extend my fingers, and my fingers are able to rotate freely about that thumb to identify that perpendicular plane or the y-plane anywhere along that axis. But in order to orientate it so that it's orientated with the y, so now I have the thumb coming towards me and the fingers extended outward, going away from the screen at an angle as well. Once my thumb's pointed in the direction of the X or I, and my fingers extended in the direction of the Y or J, my palm now pushes in the direction of the K or Z. Now I know with the X positive direction coming out of the screen and the Y positive direction coming out of the screen a little bit to the side, that the Z positive axis actually goes up towards the top of the screen, or is where my palm would be pushing upwards. You'll want to practice the right hand rule several times so that you can get comfortable given any two axes identifying the positive direction of the third, or being able to use it to apply to problems and situations. Here we see an example of a two-dimensional vector, which again, it actually has three components. It just turns out one of them is 0. This vector, represented by R, is in between the X and Y axis, so it's along that XY plane. It doesn't actually extend out of the screen or back into the screen or along the Z axis at all. So what we can get are the components along the X-axis and the components along the Y-axis. The easiest way to do that is by noticing that it forms a right triangle with an inner angle noted as alpha, the angle between the vector R and the X-axis. We can then get that X component, how much it is along that X direction, by doing R cosine of alpha. If we want to get the vertical component, since that forms a right triangle, and we still want to use alpha, that would simply be R times sine of alpha. However, if instead of using alpha, which is the angle between the vector and the x-axis, we could use beta, the angle between the y-axis and the vector, and then it would be R cosine beta to be able to get the component along the y-axis. We now have the x component that if we multiply by the unit vector I hat, we'd get the horizontal component in the component form. Or we now have the y component that if we multiplied by j hat, we'd have the y component for component form. If there was an extension into or out of the page, so there was some angle relative to that perpendicular or z-axis, and we could call that gamma, then we could use r cosine gamma to be able to get the z component and multiply that by k hat to get the third part of our component form for the unit vector. When we're describing a vector in terms of its unit vector, it's a couple things to note. One is unit vectors are unitless because they end up canceling out. Take the x component, not with the units, and simply write down the value that we get from that x component times I hat, sum that together with the value for the y component times j hat, and sum that together with the value for the z component times k hat. We also sometimes show that in bracket form, where we have r equals parentheses, and we show the x, y, and z components separately, either as the number with units, which would be the component form as it is, or in the unit vector form, where it's x, I hat, y, j hat, z, k hat. Sometimes for these brackets, instead of using parentheses, they'll use little elbow kind of greater than or less than looking things, which is perfectly legitimate. You should be able to see both and understand what is being represented. On occasion, we can also show this as a column form where we'll have the x, the y, and the z shown vertically. When we have the component form of the vector, x I hat, y j hat, and z k hat, we can actually use that to be able to get the magnitude of the vector it describes. Similar to how we would get the vector from a two-dimensional description using a squared plus b squared equals c squared, in this case, the magnitude squared equals the sum of the three components squared. X squared plus y squared plus z squared equals the resultant squared, or the square root of the sum of those squares is equal to the magnitude of the vector. In this case, we see vector b being represented in the component form in terms of its unit vector. And then we see that we can get the magnitude of that vector b by simply taking the square root of the sum of each of those components. Remember, the unit vector has a length of exactly 1 unit and points in the same direction. It's exactly proportional to the original vector that's being described. In this case, the vector b does not have a magnitude of 1, but the unit vector that describes the same direction would have a magnitude of 1. What we need to do is simply get the proportion of the sides for that triangle to be able to get what our unit vector is in each of those directions. What that means is we take the x component and divide that by the magnitude of the vector, and that gives us the unit vector in the I direction. And we take the y component and divide it by the magnitude of the vector, and that gives us the unit vector in the j direction. And if we take the z component and divide it by the magnitude of the vector, we get the unit vector in the k direction. Note that if we squared and summed up those, and then took the square root, we would get that magnitude of 1 because it is the unit vector. Using the unit vector becomes very helpful when we're trying to do several different mathematical operations with vectors. Having these unit vector forms is going to be quicker than having to use trigonometry or having to use a graphical method where we draw the vector's tail to tip every time we're trying to get their sum. However, that's going to make a lot more sense to you when you see some example problems of how we can use these unit vectors